Hi, welcome back to our review videos on rational functions. So one of the things that we're going to do today, we're going to start with a jump start, something to get you going based on the video that we did on Wednesday. So on this video, the first thing that you're going to do is you guys are going to try, given the rational function below, you are going to, sorry, get my keyboard out of the way. You are going to rewrite the function in factored form for both of these. Identify the restricted values using the denominator, setting it equal to 0, reminding you of what you're supposed to be doing, and then write your domain in a correct set notation. And I don't know about you, even though I like interval notation, it is certainly faster to use set builder. Then tell me what the zeros of the function are using the non-canceled factors of the numerator. In other words, ask Fred. And then what is the y-intercept of the function? And again, you could also ask Fred for both of these because he will be much simpler, and that will be kind of what we're looking at. So I'm going to go ahead and pause right here, let you guys work these two problems for a jump start, and then throw up some questions into the Edpuzzle. Okay, guys, coming back in, you can certainly check your answers with the key as well as with the questions that I popped up. I'll put some responses in there for you, but pretty straightforward things. The only thing I think I might add to this is this idea that, like, if you were checking, just to kind of add into the graphical nature of this to review what we did last time, remember that if I were to do f of -1, now, it is undefined, but there's a lot of times where we are interested in finding what the actual form of that undefined is. And so we do kind of want to make sure that we are seeing the form and then making a decision about what's happening on the actual graph of the rational function. So f of -1, if I were to plug that in, now, recognize that I can tell from Fred that it was not removable, that we still have that x plus 1 factor in the bottom. And if I were to plug that in, that what I would get in that is going to be, like if I plug it into the original, I would get 3, whoops, sorry, am I writing here? 3 plus 7 minus 6 over 0, which is going to give me 4 over 0. So we see that, of course, this is undefined. If I just ask you to evaluate, then kind of clearly when we're looking at that, we definitely want to kind of show that it's undefined. I mean, if I just ask you to evaluate it and I'm not really interested in these forms, then what you're going to see is that it's okay that you can go directly from the f of -1 to the undefined. Well, what my point is when we're taking a look at this is that it's very important to know what the form is because that tells us what's happening on the graph. And hopefully you'll remember that if you see something of the form non-zero over 0, that that's going to be a vertical asymptote. All right, I'm just going to write, therefore, my computer, as always, is lagging, but x equal to -1 is a vertical asymptote, and there is a infinite discontinuity. All right, and then the other one, let's take a look at the form of the second one that we have. Like I said, I'm just going to squeeze it down here at the bottom. If I did f of 3, of course it's undefined because I was able to remove it. But when I plug 3 in, we're going to get, what, 27 minus 21 minus 6 over 0, which is going to be 0 over 0. Again, it's certainly equal to undefined. If I was just asking you to evaluate this, you can go directly from f of 3 equals undefined. But if I'm asking you to think about the form of what that undefined is, it is the indeterminate form. So x equal to 3 is a whole on the graph, and it's a point discontinuity. So if I ask you for the type of discontinuity, we would say point discontinuity. If I ask you for what's on the graph, you would say hole. So just make sure you answer the question that I ask. Right, so from there, you have this homework practice down here. So that's going to be part of your homework tonight, is to do practice on this. So hopefully if you have any questions, you can shoot me an email, but we're going to move on to the next video. Or actually, we're going to stay in this video, and we're just going to move on to the next set of class notes. Okay, so coming into our class notes here on discontinuities of rational functions, I'm going to remind you of what those different major types of discontinuities are. So as we take a look at this, and we've been using this kind of terminology all along, that there are really two types of discontinuities, and those two types are removable and non-removable. Removable are the ones that, like we saw with rational functions, that because of some algebra technique, we can remove the bad guy factor from the denominator, which would then allow us to remove the division by zero problem, which would allow us to then basically have a point discontinuity on the graph. And then we have the non-removable discontinuities, and non-removable ones are the ones that we cannot remove. Now, there are different kinds. Now, with rational functions, you pretty much only have two types. The two types that you would have in rational functions are going to be the point and the infinite discontinuities. Those are the only ones that really occur in a polynomial divided by a polynomial. But since we were talking about types of discontinuities here, I did want to go ahead and kind of talk about all the different types of discontinuities. So coming down here, let's take a look and let's define each of these types that are there. All right, so description of the graph, a point discontinuity, two pieces of your graph are going to meet in a single point, hence point discontinuity, and that point is a hole. So two pieces meet at an open circle on the graph, quote unquote, a hole. Right? And then the difference about the infinite discontinuities that we saw, there are two pieces of the graph, two pieces that don't meet, that do not meet. And the reason that they don't meet is because the function f of x goes or approaches, I like that word better, plus or minus infinity. And so those are the ones that are the vertical asymptotes that you see on the graph. And so if you see a hole in the graph, then we know we have a point discontinuity. If you see a vertical asymptote on the graph, then you know that you have an infinite discontinuity. Now let's talk about the jump discontinuity. Now the jump discontinuity is also two pieces that do not meet. And when we look at that, those two pieces that do not meet, the reason that they do not meet is because f of x approaches, I'm going to use that word, approaches different y values as x approaches a single number, and I'm going to call that single number c. All right, so two pieces that do not meet because f of x approaches a different y value. And you're going to see the graphs below. They're going to show the illustration of this. But as x goes to a single number, the two graphs, and they could, I mean, basically all of these here will say as x approaches c, as x approaches c. We'll add that in for all of these, and hopefully this thing will sync for me, syncing here right now. But as x approaches a single value, what you will see is that they will do different things. As the function, as you're plugging in values closer and closer to x equal to c, you could meet in a point. That's point discontinuity. It's a hole. It's going to be missing, but it's going to be, so it's a discontinuity. That's a gap in the graph, but it's only a single point that's missing. They could have a vertical asymptote and either go up or down. They could both go up. They could both go down. Either way, there's a vertical asymptote in the graph. Or as you're heading, as the x values are heading toward that c, they don't meet, they head, they don't go up to infinity, they don't go down to negative infinity, they just have a gap, and that gap is a gap in y values. They're directly above each other. And so you can see right here, if I kind of scroll down and take a look at this, you can see that the value of c that we're looking at for this first one, the c value is 1. So as x approaches 1, both pieces of the function here and here are approaching the same point, the same y value of 1. So that's a point discontinuity, but it's a discontinuity because I'm missing the point. There's a hole there. Then over here, we have a vertical asymptote, and you can see as x approaches, again, same value, x equal to 1. As x approaches x equal to 1, the left-hand side goes up to infinity, the right-hand side goes down to negative infinity, and that's called an infinite discontinuity. And then as you look at this piece right here, two pieces, you're heading toward x equal to 1, but as x is heading toward 1, then you see that you have a jump in the y values. So it goes from a piece down here, then there's a gap in the y values, and it starts up here. And so that's kind of one of those things that shows you it's a jump in y values that you're looking for. Now, I did want to do the last one that's here. And the last one, and this has to do with things like where you have square roots and those kinds of things, that when you have basically a gap or region of x values with no graph, that's the indication that you have a regional discontinuity. Things like square roots or logs. And an interesting thing, like a log graph, if you recall from when we were doing log graphs, a log does have a vertical asymptote at x equal to 0. So it does have an infinite discontinuity at x equal to 0, but it actually has a regional discontinuity for all the negative numbers because there's no graph for the negative numbers. So that kind of gives us different things that we're looking at with that. Just for practice, will you guys go ahead and fill in your domain and range down here below these, just a little extra practice on that, and then we'll continue on with these notes. All right, so taking a look at these, we do want to kind of have this idea. Notice that here in these first two, like when you're missing a single value from the domain, we know that we have a discontinuity because we have a restriction. There is an x value not included. However, we won't know what type of discontinuity it is, whether you have a missing point, whether you have an asymptote. And even though right here in this one, even though the domain on this one was negative infinity to infinity, I certainly could have a hole in this location right here and have exactly the same domain. And so I could also have a jump discontinuity at a single value that's missing. So that's why we have to do a little bit more than just looking at domain to determine what type of discontinuity we have. And also kind of if you look at all of the first three, especially, the range covers everything. I'm assuming that these ends continue to go to infinity and continue to go to negative infinity, that the behavior of the graph follows the trend that you see with the arrows. So it's the idea that, there are times where your domain will clearly show that you have a discontinuity. If there is a restriction, there is a discontinuity. But sometimes you can have a domain that includes all real numbers, but yet you still have a discontinuity. So that's one of those kind of statements that all restrictions are discontinuities, but there are discontinuities that are not actually restrictions on the functions. This would be an example from like a piecewise function that we're looking at. And of course, this is an example from a square root, taking a look at that. All right, finishing up this video, what you're going to do in between this video and the next, you're going to use the graphs that you have on this page right here to then answer the questions that are right here in the chart. And once you have answered these questions, you're going to go here and based on the information gathered in the table on the previous page, what inferences can you make about connecting the equation to the location of the discontinuities? So do that and then come back in for the second video on discontinuities.